The universe is expanding, but not the way scientists predicted, and it's a big problem. For decades, physicists have been measuring how fast the universe is growing, and depending on how you measure it, you get two completely different answers. Not slightly different, not close enough to chalk up to human error, genuinely, frustratingly, embarrassingly different. And nobody, not the brightest minds alive today, can fully explain why. Now, I've spent a lot of time thinking about hard problems. And I'll tell you something, the most exciting problems in physics are never the ones we've solved. They're the ones that make us sit back and say, wait a minute, something here doesn't add up. This is one of those problems. In fact, this might be the biggest one we're staring at right now. Let me take you through it the way I think about it from the very beginning. Let's go back to 1929. Edwin Hubble, brilliant observer, careful experimenter, is looking through his telescope at distant galaxies, and he notices something remarkable. The light coming from those galaxies is shifted toward the red end of the spectrum, and the farther the galaxy, the more the shift. Now, what does that mean? It means those galaxies are moving away from us, and the farther they are, the faster they're moving. This is what we call Hubble's law, and it told us something stunning. The universe is not static, it's expanding. Every galaxy is moving away from every other galaxy, like raisins in a loaf of bread rising in the oven. The raisins don't move through the bread itself is expanding. That's the universe. Space itself is stretching. Now, to describe how fast this is happening, physicists came up with a number. We call it the Hubble constant, written as h0, h0. It tells you the rate at which the universe is expanding. Specifically for every megaparsec of distance, and that's about 3.26 million light years. How many kilometers per second is the universe expanding? Simple enough concept. You'd think we could just measure it, and we can. The problem is, when we measure it two different ways, we get two different answers. Let me explain the first method. This is the one astronomers call the distance ladder. It's a method built from the ground up, using actual observations of actual objects in our local universe. It works in steps. First, you measure nearby stars using parallax, the way a star appears to shift position as the Earth moves around the sun. Simple geometry, completely reliable. Then, using those nearby stars as a foundation, you calibrate a special type of star called a Cepheid variable. These stars pulse. They brighten and dim in a very regular rhythm. And the key discovery made by Henrietta Swan Leavitt in the early 1900s was that the period of that pulsation directly tells you the true brightness of the star. So if you know how bright it truly is and you measure how bright it appears, you can calculate the distance. Beautiful idea. Then, using Cepheids to calibrate distances to nearby galaxies, you can go even further, to a class of stellar explosions called type Ia supernovae. These are extraordinary objects. When a white dwarf star accumulates just enough mass from a companion star to tip over a critical threshold, it explodes. Every single time, it explodes with almost exactly the same intrinsic brightness. So again, you know the true brightness. You measure the apparent brightness, you get the distance. And because supernovae are so blindingly luminous, you can see them across enormous cosmic distances. When you put all of this together, parallax to Cepheids to supernovae, and use that chain to measure the expansion rate, you get a Hubble constant of roughly 73 kilometers per second per megaparsec. 73. Write that down. Now let me tell you the second method. This one doesn't look at the nearby universe at all. It looks all the way back to almost the very beginning. About 380,000 years after the Big Bang, the universe cooled down just enough for protons and electrons to combine and form neutral hydrogen atoms. Before that moment, the universe was an opaque, glowing plasma. Light couldn't travel freely, but the moment those atoms formed, the universe became transparent. Light could finally move, and that light, stretched and cooled by billions of years of cosmic expansion, is still traveling through space today. We call it the cosmic microwave background radiation, the CMB. It was discovered accidentally in 1965 by Arno Penzias and Robert Wilson. They kept finding this persistent noise in their radio antenna and couldn't get rid of it. Turned out to be the afterglow of the Big Bang. They got the Nobel Prize for it. Now, the CMB is not perfectly uniform. If you map it carefully across the sky, it has tiny temperature fluctuations, small hot and cold spots. And those patterns carry an enormous amount of information. They tell us about the density of matter and energy in the early universe, the geometry of space, and yes, the expansion rate. When cosmologists take those CMB measurements and feed them through the standard model of cosmology, a model called lambda CDM, they calculate a Hubble constant of roughly 67 to 68 kilometers per second per megaparsec. 67, not 73, 67. That difference, 67 versus 73, is what physicists are calling the Hubble tension. And I want you to understand why this is not just a rounding error. In physics, when we say something is a tension, we have a precise way of measuring how serious it is. We use something called sigma, the number of standard deviations separating two measurements. 1 sigma, barely worth noticing. 2 sigma, mildly interesting. 3 sigma, people start paying attention. 5 sigma. In particle physics, that's the threshold for claiming a discovery. The Hubble tension is currently sitting at roughly 5 sigma. 5. That means the probability of this discrepancy arising purely from random measurement error is something like 1 in 3.5 million. This is not a statistical fluke. This is not a systematic error that someone left in by accident. Both measurements have been checked, rechecked, and checked again by multiple independent teams using different instruments, different techniques, different calibration methods, and they keep getting the same answer, 2 different answers. Something is genuinely wrong. Either our measurements are flawed in some way we haven't identified, or our understanding of the universe is incomplete. And the second possibility is far more interesting. Now I want to spend a moment on something that I think gets overlooked in these discussions. People talk about the Hubble tension as if it's purely an observational puzzle, but it's also a theoretical puzzle. And the theory at stake here is one of the most successful in all of science. The lambda CDM model, the standard model of cosmology, is built on a few key ingredients. Lambda refers to the cosmological constant, which represents dark energy, the mysterious force accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible gravitational scaffolding around which galaxies formed. Together with ordinary matter, radiation, and general relativity, this model explains an astonishing range of observations: the CMB, the large-scale structure of the universe, the abundance of light elements formed in the first few minutes after the Big Bang. It works beautifully, except now it's predicting an expansion rate that disagrees with what we directly measure nearby. And that is a serious crack in an otherwise stunning edifice. Let me take you through some of the possible explanations because I think this is where things get genuinely fascinating. The first possibility is mundane but worth taking seriously. Maybe there's still a systematic error hiding in the distance ladder. Some step in that chain, parallax, Cepheids, supernovae, might have a subtle bias we haven't caught. Maybe the Cepheid calibration has a small error that gets amplified when you use those Cepheids to calibrate supernovae, and then amplified again when you use supernovae to measure distant expansion. Errors can compound. This has been studied extensively. Teams have gone back and used completely independent distance indicators, including a type of old pulsating star called a tip of the red giant branch, or TRGB, to check the supernovae calibration. The James Webb Space Telescope, launched in 2021, has made new, sharper observations of Cepheid variables in nearby galaxies, trying to identify whether blending effects, where nearby stars get merged together in older, lower-resolution images, might be inflating the measured distances. And the answer keeps coming back. Yes, there are small corrections to be made, but no, they're not nearly large enough to resolve the tension. The number keeps coming out close to 73. So if it's not systematic error, then perhaps the physics is genuinely new. Here's one idea that I find particularly elegant in its simplicity, and suspicious for exactly the same reason. What if dark energy is not constant? In the standard model, the cosmological constant lambda is just that, a constant, a fixed amount of energy density baked into the fabric of space. But what if it's not fixed? What if dark energy changes over time? Maybe it was stronger in the early universe and has since weakened. Or the opposite, maybe it's growing stronger. If the energy driving cosmic expansion was different in the early universe than it is today, then the CMB-based calculation, which extrapolates forward from the early universe using a fixed lambda, would give you a wrong answer for today's expansion rate, and the direct measurements, which observe the nearby universe as it actually is today, would give you the true current rate. The tension would then be pointing us toward the evolution of dark energy over cosmic time. Interestingly, there was a result in 2024 from the Dark Energy Spectroscopic Instrument, DESI, which mapped millions of galaxies across the universe to study the expansion history. Their early data showed hints, not conclusive but intriguing hints, that dark energy might not be constant, that it might be evolving. This sent a buzz through the cosmology community because if true, it would be one of the most significant discoveries in physics in decades. The data is still coming in. The jury is still deliberating, but it is exactly the kind of hint that makes you feel like you're on the edge of something. Here is another idea, one that I find deeply interesting because it operates entirely in the early universe. It's called early dark energy. The logic goes like this. Suppose there was a brief period before recombination, before that moment when the CMB was released, when an extra form of energy existed in the universe. Not the dark energy we see today, but a different component that was active for a short time and then faded away. This early dark energy would have slightly accelerated the expansion of the universe before the CMB was released. If the universe was expanding faster in that early period, the sound horizon, the characteristic scale imprinted in the CMB temperature fluctuations, would be smaller. And if that scale is smaller than the standard model assumes, then the distances inferred from CMB observations would shift, pulling the estimated Hubble constant upward closer to 73. It's a genuinely clever idea, and it can work mathematically. The problem is that it creates other tensions. It tends to worsen the agreement between theory and observations of the large-scale structure of the universe, particularly something called the S8 tension, which is a separate disagreement about how clumpy matter is in the universe. Solving one problem while creating another is not what we're looking for. We want a single coherent picture. We don't have one yet. Let me tell you about another possibility, one that's more radical and which I think deserves a serious hearing. What if the universe is not as homogeneous as we assume? The standard model of cosmology is built on a principle called the cosmological principle. The idea that on the largest scales, the universe is roughly uniform, the same in all directions, the same in all locations. And on enormous scales, this appears to be true. But what if we happen to live in a region of the universe that is slightly less dense than average? A local underdensity, and sometimes called a void. If we're sitting inside such a void, then the expansion rate we measure locally, using supernovae and Cepheids in our cosmic neighborhood, could be somewhat higher than the global average. Mass slows down expansion. Less mass nearby means slightly faster local expansion. So a local void would push our measured Hubble constant higher than the true global rate. The idea is not crazy. We know the universe has structure. There are dense clusters and filaments, and between them, large voids. The question is whether the void we might inhabit is large enough, deep enough to produce a 5 sigma discrepancy. Most analyses suggest the required void would be unusually large and deep, statistically unlikely but not impossible. There is yet another class of ideas, more exotic, that I feel obliged to mention because they're theoretically interesting, even if observationally unconstrained. These involve modifications to gravity itself. General relativity, Einstein's masterpiece, is the foundation of modern cosmology, and it has passed every experimental test we've thrown at it, from the precession of Mercury's orbit to gravitational waves from colliding black holes to the bending of light around massive objects. It is one of the most well-tested theories in physics, but what if it's not exactly right on cosmological scales? What if gravity behaves slightly differently across the vast distances of the universe than it does locally? Several modified gravity theories have been proposed, and some of them have enough free parameters that they can, in principle, accommodate a higher local Hubble constant. The trouble is that many of these theories predict other deviations from general relativity that we should be able to observe, and so far we don't. I want to pause here and say something about how science actually works, because I think it matters for understanding why the Hubble tension is such a serious issue. In physics, we don't demand perfect theories. We demand theories that make precise, testable predictions. The standard model of cosmology makes a specific prediction about the Hubble constant, about 67, derived from first principles and early universe observations. The distance ladder measurements say the answer is 73. That's a falsifiable disagreement. That's exactly the kind of thing science is supposed to resolve. And the way you resolve it is not by deciding in advance which measurement you trust more. You do more experiments, you bring in independent methods, you look for internal consistencies, you try to break your own result before someone else does. And you stay genuinely open to the possibility that something in your theoretical framework, something you thought you understood, is wrong. That is the honest scientific posture. And right now, that posture demands we take the Hubble tension very seriously. Let me tell you about a few of the newer methods that have entered this arena, because the distance ladder and CMB are not the only players anymore. One of the most exciting developments of the last decade has been the use of gravitational waves as a new kind of distance measurement. When two neutron stars spiral together and collide, they emit gravitational waves, ripples in spacetime, and also a burst of light. The gravitational waves tell you directly how far away the event is, based purely on the physics of the inspiral. The light tells you the redshift, how fast the host galaxy is moving away from us. Put them together and you get the Hubble constant. No calibration chain, no intermediate rungs, pure physics. In 2017, we detected exactly such an event, a neutron star merger called GW170817. The estimated Hubble constant from that single event was about 70 kilometers per second per megaparsec, right in between the two disputed values, tantalizingly in the middle. But a single event carries large statistical uncertainty. As we accumulate more gravitational wave detections with optical counterparts, which LIGO, Virgo, and future detectors will provide, this method will sharpen dramatically. Within the next decade, it could be precise enough to definitively side with one value or the other, or it might split the difference and force us into completely new territory. Another independent method uses something called time delay cosmography. When a distant quasar, an extremely luminous object powered by a supermassive black hole, sits behind a massive galaxy, the gravity of that galaxy bends the light. Multiple images of the quasar appear around the galaxy. If the quasar varies in brightness, those variations show up in each image at different times, because the light takes different paths of different lengths. By measuring those time delays precisely and modeling the lens carefully, you can infer a distance, and from that, the Hubble constant. Current measurements from this method, run by a collaboration called Heterolecau, tend to favor higher values, closer to 73. But there are ongoing debates about how sensitively the answer depends on assumptions about the distribution of dark matter within the lensing galaxy. These independent methods are crucial because if they converge, if gravitational waves, time delays, surface brightness fluctuations in galaxies and other approaches all point in the same direction, then we'll know which side of this argument to trust. Now, I want to step back and give you the biggest possible perspective on this because I think the Hubble tension is actually part of something larger. We live in a remarkable era for cosmology. In the past 30 years, we've learned that ordinary matter, the stuff you're made of, the stuff stars are made of, the stuff we can see, accounts for only about 5% of the total energy content of the universe. Another 27% is dark matter. We know it's there from its gravitational effects, but we have no idea what it is. And the remaining 68% is dark energy, the cosmological constant, the energy of empty space, which we know is driving the accelerated expansion of the universe and which we understand even less. Think about that. 95% of the universe is made of stuff we fundamentally do not understand. Now comes the Hubble tension, telling us that even the framework we've been using to describe that mysterious 95%, the lambda CDM model, may have a crack in it. And then there's the S8 tension I mentioned, which involves how matter clusters together in the universe. And there are emerging questions about whether the universe is truly isotropic, whether it looks the same in all directions, based on some anomalous patterns in quasar distributions and CMB measurements. We might be on the edge of a genuine paradigm shift, or we might find a mundane correction that patches everything up. I don't know which. Nobody does. And I'll be honest with you, not knowing is exactly what makes this exciting. I want to tell you something that I think about often and that I think should be said plainly. When I was working on quantum electrodynamics, the theory of how light and matter interact, we kept running into infinities, infinitely large answers showing up in our calculations, which clearly couldn't be right. The response of most physicists at the time was to get uncomfortable and look away. The infinities were embarrassing, but those embarrassing infinities were pointing at something real. They were telling us that our theory was incomplete, that it was valid only up to a certain scale, that new physics was lurking at higher energies. The infinities weren't failures of the theory, they were messages. The Hubble tension feels like a message. The universe is telling us something. Maybe it's telling us that dark energy is not constant. Maybe it's telling us that there was new physics in the early universe we haven't accounted for. Maybe it's telling us that our theory of gravity needs a revision on cosmological scales. We don't know yet, but we should listen carefully instead of dismissing it. Let me also address something that comes up in popular discussions of this problem, which I find a little misleading. People sometimes say things like, "Scientists are confused about the universe." As if that's a sign of failure. I want to push back on that hard. Confusion is not failure. Confusion is the entry point to discovery. Every major breakthrough in physics has been preceded by a period of deep confusion, when the old framework was clearly straining against new data before the new framework had been found. The ultraviolet catastrophe in the late 1800s, where classical physics predicted that a hot object should radiate infinite energy, was deeply confusing, and it led directly to quantum mechanics. The failure of the Michelson-Morley experiment to detect the luminiferous ether was deeply confusing, and it led directly to special relativity. The precession of Mercury's orbit, which Newtonian gravity couldn't quite explain, was a small but nagging confusion that Einstein eventually resolved with general relativity. The Hubble tension might be our ultraviolet catastrophe. It might be our Michelson-Morley, a 5 sigma discrepancy between two precise measurements of the same fundamental constant of nature. This is exactly the kind of crack in the foundation that new physics seeps through. If I were a young physicist today, and I will tell you there are moments when I wish I were, this is the problem I would want to work on. Not because it's easy, because it's hard. Not because the answer is obvious, because it isn't. There is something hiding in the gap between 67 and 73, and whatever it is will probably require us to revise something we thought we knew. Maybe the revision will be modest. Maybe it will be like adjusting a parameter in the cosmological model, tweaking the equation of state of dark energy, or adding a small early dark energy component, and lambda CDM will continue to stand slightly amended. That's one possibility. Or maybe, and this is the possibility that really keeps cosmologists up at night, maybe the resolution will require something genuinely new, a new form of energy, a new understanding of gravity, a new ingredient in the cosmic recipe that we haven't imagined yet, something that doesn't fit in the existing framework at all, the way quantum mechanics didn't fit in the classical framework, the way general relativity didn't fit in the Newtonian framework. Physics has been here before, and every time the resolution was more beautiful and more surprising than anyone expected going in. The James Webb Space Telescope, now operating at its Lagrange point 1,000,000 miles from Earth, is giving us sharper views of sea feeds and other distance indicators than anything we've had before. The Vera Rubin Observatory, coming online in the next few years, will survey the southern sky in unprecedented depth, mapping the large-scale structure of the universe with extraordinary precision. The DESI survey is continuing to accumulate data on how the universe's expansion has evolved over cosmic time. LIGO and its successor detectors are accumulating more gravitational wave events. The Euclid Space Telescope, launched in 2023, is mapping the geometry of the universe with weak gravitational lensing. All of these instruments are aimed in one way or another at this problem. The data that will resolve the Hubble tension or deepen it further is being collected right now. The answer might come in 5 years, it might come in 20, but it will come. And when it does, it will be because someone sat with the data long enough, thought about it carefully enough, and had the courage to say, I think the way we've been thinking about this is wrong. Here's a better idea. Let me show you the calculation. Let me bring this to a close the way I believe it deserves to be closed. The universe is approximately 13.8 billion years old. It began as an extraordinarily hot, dense, compact state, smaller than an atom, and has been expanding ever since. We have figured out in the span of 100 years of modern physics and astronomy an enormous amount about how this happened. The sequence of events from the first fraction of a second after the Big Bang to the galaxies and clusters and voids we see today, that is a staggering intellectual achievement. And yet, Two independent, carefully cross-checked measurements of the simplest descriptor of that expansion, how fast it is happening right now, disagree by 5 standard deviations. The universe is expanding wrong, or rather, we are understanding it wrong. Somewhere in our framework and in our measurements, in our models, in our assumptions, there is an error, and that error is a door. Doors are interesting. What is on the other side of this one, we do not yet know, but I promise you, it is worth finding out. The history of physics is littered with cases where a small, embarrassing discrepancy turned out to be the gateway to something profound. And 5 sigma is not small. Pay attention to this one. It matters, not just for cosmology, but for our fundamental understanding of what the universe is made of, how it began, and where it is going. The universe has been trying to tell us something. We just haven't learned to read it yet, but we're getting closer. Every measurement, every new instrument, every young physicist who looks at this problem and refuses to accept close enough gets us a little closer, and that, to me, is what science is.